in this second part of the lecture, I want to talk about normal instance of a wave onto a conducting surface. And imagine that you have a conductor on your right hand side, labeled as the second material, material 2. And on the left hand side, you could have an unbounded vacuum or a piece of the dielectric. So this is the conducting boundary right here. And you send an electromagnetic wave toward the z direction plus z direction. And then you will be expecting to have some reflected component in the backward direction. But we said that in the perfect conductor, the electric field and magnetic field have to be equal to 0. So you will not expect any field inside this conductor. Therefore, there's no transmitted wave in the forward direction inside this piece of the conductor. The first step, as I just said, that we want to write down all the field expressions. And in this configuration, you can arbitrarily set the polarization along, say, this direction, or any direction perpendicular to the z direction. And from this configuration, apparently, the wave is a TEM wave, transverse electromagnetic wave. So let's just choose the polarization of the instant wave along x direction. And I set it along this upward direction to be the x direction. And in this region, there will be a reflected wave with the electric field. So we also write down an x polarized reflective field with the amplitude equal to ER0. And because there's no factors, there's no reason that the wave will change polarization direction. So in this reflective field, we also specify the polarization along x direction. Once you have the electric field expression, then we can use this formula we learned before to calculate the instant and also reflective magnetic field given by this expression. And you see that when we do this calculation, the magnetic field flip side in the AY direction when we calculate the field component for the reflective wave, because the propagation direction of the reflective wave is along minus z direction. So you can see that there's a minus sign for the forward propagating wave in this plot, and there's a plus sign before this J for this backward propagating components. And we don't need to care about the field inside this piece of perfect conductor, because we know that no electromagnetic field can penetrate through a perfect conductor. So now we go to the step 2. We want to measure boundary conditions and figure out the unknown components of the field. And the total field, electric field in this region is going to be the summation of the instant field plus the reflective field. So we write down the field like this. Just copy the expression from the last page. This is the forward propagating electric field, and this is the reflected electric field. And the sum of them are polarized along the x direction. And the boundary condition require the tangential component of the electric field to be equal to 0. But you know that the electric field inside this perfect conductor is equal to 0. So you just equate this to be equal to 0. And then you come up with the result for the reflective field component, which is the minus the instant field EI0. So now you express the reflective field component as a function of the instant field component. And in the region z less than 0, which is the region on the left hand side, you can now just write down the total field like this, because you already solved for this unknown ER0 in terms of EI0. So just group them together, and then you will end up having this expression for the phasor field on the right hand side. And it's interesting that you see this expression is independent of time, because you have a sine kz. And if you still remember the standing wave expression from the transmission line, then you know that this is a standing wave in this region. And you can also write down the total magnetic field in this region, because previously we already expressed this magnetic field in terms of the electric field. So the result is like this. And you can see that you also have a term cosine kz, which is independent of time. So what happened is that if you send a wave with normal instance onto this conducting surface, and you're going to see the wave gets reflected back, and nothing can penetrate into this perfect conductor. So with the phase expression of the electric field, you can convert it into the real expression by multiplying the phase expression with exponential j omega t, and then take real part of it. Once you do this step, then you have the real expression of the electric field in this region. And again, this term sine kz is independent of time, and but you have a sine omega t that change over time. So if you plot the field in this region and allow the time to tick, then you'll see this standing wave pattern forming on the left-hand side of this boundary. And this is something you are familiar with when you learn about the transmission line. This is 100% contrast standing wave, and at this node, it's always fixed at 0. And between nodes, you have the big amplitude oscillating up and down. And this electric field is proportional to sine kz, and this sine kz gives you the periodicity of this field pattern. So the between two nodes, the separation of the distance is going to be equal to half of the wavelength. And this is something you also learned about a long time ago. For standing wave, the separation between the nodes is equal to half of the wavelength. And we can also plot the field pattern for magnetic field. And so if we convert the phasor expression of the magnetic field to a real expression, then you can also see this cosine kz in this expression, which is independent of time. It just tells you that this pattern is fixed in space and does not change over time. But the amplitude is modulated with the sinusoidal time variation. So if you allow this time to go, then you will also see this standing wave pattern. And again, the separation of the two nodes, or the separation of the two peaks, will be equal to half of the wavelength. But because you have a cosine here, so on the boundary, you have the maximum magnetic field. Unlike last page, you have the minimum for the electric field at the boundary, because the tangential component of the electric field have to be continuous across the boundary, and it happens that on the right hand side, the electric field is equal to 0. So the electric field pattern and magnetic field pattern are different, and the phase in fact changed over like 90 degrees. And you can also deduce the surface current on this boundary, because you have a maximum magnetic field on this boundary. So from this calculation, you are also expecting big surface current on this conducting boundary. So now I plot the electric field together with the magnetic field patterns, so you can make a comparison. And you see that on the surface, the magnetic field is maximum, and there's the surface current on this boundary. But on this surface, you don't have the tangential component of the electric field. So it turns out that you have a nodes for the electric field on this boundary. And you can see that because of this 90-degree phase shift, the maximum point for the magnetic field corresponds to the node location of the electric field, and vice versa, which means that if you have a maximum amplitude for this electric field pattern, then the location will be matched to the node of the magnetic field pattern. So it's also interesting to see the time average power in this standing wave. And by definition, for a standing wave, you have a component propagating in one direction, and then you have also the wave propagating in the opposite direction. For 100% contrast standing wave, then you'll be expecting that there will be an equal amount of power propagating in the forward direction and backward direction. So without doing detailed calculation, you'll be expecting the total time average power in this standing wave pattern will be equal to 0 because the equal power propagating in the opposite direction. And indeed, if you pick up this formula to calculate the time average power, which is the real product of the electric field phasor times with the complex conjugate of the magnetic field phasor divided by 2, you'll be getting nothing because the phasor expression for the electric field is here, and the phasor expression for the magnetic field is here. And it turns out that you see a J in this expression, and you have the real value for this one. When you pick up the real product of the multiplication of these two, you don't have the real product. You just get nothing. And this just tells you that in electromagnetics, when we talk about power and also the energy propagation, we need to take into account the direction of the propagation. So finally, I want to give you a little bit summary. 所以在这个小节里头，我们介绍了这个垂直入射的状况。那我们知道，这个当一个这个边界是由这个真空或者是介电物质跟导体两导体组成的时候呢，在两导体里头，它的电场跟磁场会是等于0。所以呢，这代表说这个电磁波没办法穿透这个良好的导体。所以我们不需要去计算这导体里头的这个电磁场的强度是多少，因为它们就是等于0。那所以呢，这个在一个理想导体的这个边界上头，所有的波全部的能量都会反射，形成一个100%的一个驻波的状况。那在这个表面上呢，在这个边界的表面上头，你的磁场会是最大值，因为在这个表面上头会产生一个表面电流。那但是呢，这个tangential component of electric field， 也就是切线方向的这个电场呢，会等于0。那这个所以在这个磁场跟电场的这个场态的这个相位上头呢，会差了90度。所以这就是在我们在探讨一个电磁波垂直入射导体的时候会发生的状况。谢谢。